Hi students, hope everyone is fine and safe. It gives me immense pleasure to welcome you all to my new video, and today's video is about another interesting topic in 8086 microprocessor. We're going to see pin diagram of 8086 microprocessor. Right, in this video we will see in detail about the 40 pin diagram of 8086 microprocessor. Right, so this is the pin diagram of 8086 where we have already seen the basic features of 8086, and we have also seen the register organization of 8086, right? And in this video we're going to see only the pin diagram. I'll explain in detail about each and every pin. Now we'll see each pin in detail. I'm just going to revise whatever I said, right? As I said, from 80 815, you can see here from 80 to 815 address data lines, it is bidirectional, right? And depending upon the ALE signal, it can be used as an address bus and data lines, right? And this is time multiplexed memory IO address and data bus, and it acts as an address bus during the first part of the clock cycle and data bus for the remaining part of the mission cycle, right? And you can see these four status lines, the address line and the status line, where the address line and status lines are time multiplexed, and during T1 it will act as a higher order bit address, and in remaining clock cycle it will be acting as a status signal, right? And coming to this status signals, S6 will always be 0 and S7 will always be 1, right? So we don't want to worry about this two signals, whereas S3 and S4 will tell you which segment we are going to access, right? So which segment we are going to access, that is, you can see here, if it is 0 0, then extra segment is accessed, and if it is 0 1, it stack segment is accessed, and if it 1 0, code segment is accessed, and if it is 1 1, data segment is accessed. I already explained in previous video what is code segment, what is data segment, what is stack segment, and what is extra segment, right? And apart from it, the S5 indicates the interrupt enable flag, right? It will tell you the status of the interrupt enable flag. And BHE is nothing but bus high enable. It will tell you whenever there is a transfer of data in higher order bus, as I said, from D8 to D15, right? So that is bus high enable. Whenever there is an higher order data bus, whenever there is a transfer of data in higher order data bus, that will be enabled in this particular pin, right? And read pin, as I said, whenever the read signal, right, is initiated, like we can able to read the data from the memory. And similarly, the ready pin, as I said, it will halt the microprocessor. It will halt the microprocessor to a wait state to synchronize with the peripheral devices.
When the pin is high, it indicates the device is ready to transfer data, and when it is low, the microprocessor will enter into the wait state so that it can able to synchronize properly with the peripherals. And the next very important pin is pin 21, which is reset pin. Whenever this pin is active, whenever this pin is high, the microprocessor will enter into the reset mode. That is, it will stops the current activity and it will enter into the reset mode, where after entering the reset mode, the execution will start from this particular location, FFFF0H. Right, but one thing, the 8086 microprocessor will enter into the reset mode. That is, it will we can reset microprocessor only if this pin is 1, that is, it is actively 1 for at least 4 clock cycles. Only then we can able to reset the microprocessor, right? And the next important pin is interrupt pin, which is INTR pin number 18, and it is a level triggered maskable interrupt, and this is very important interrupt in 8086, and this is related to the interrupt flag. Whenever there is an interrupt from any peripheral device, this pin will be enabled, INTR pin will be enabled, but it doesn't mean that whenever the INTR pin is equal to 1, the interrupt will be served, right? The interrupt will be served only if the IF flag, that is the interrupt flag, if it is 1, only then the interrupt will be served, which means if INTR pin is equal to 1 and if IF flag is equal to 1, only then the corresponding interrupt will be served by the 8086. If INTR is equal to 1, if there is an interrupt, but interrupt flag is not enabled, then that particular interrupt will be ignored, right? And it is sampled during last clock cycle of each instruction if the processor enter into the interrupt service routine or not, right? So this pin, interrupt pin, will tell you whether there is an interrupt or not, right? But that interrupt will be served only if IF flag is equal to 1, right? And the next important interrupt is NMI interrupt, which is positive edge trigger interrupt, whereas the INTR pin is level edge trigger interrupt. And NMI interrupt, that is non-maskable interrupt, is the high priority interrupt in 8086, and it cannot be masked using software, right? And it causes type 2 interrupt. And these are the two interrupts in 8086. The next pin is pin number 23, which is test pin. This is very similar to the ready pin. Even the test pin also makes the microprocessor to enter into the wait state, similar to the ready pin, right? Whereas in ready pin, the microprocessor enter into the wait state only because to synchronize with the peripherals. But here, the microprocessor enter into the wait state in order to synchronize with the normal program execution, right? So that is the internal program execution. To synchronize with the internal program execution, the microprocessor will enter into the wait state, and that will be taken care by this test pin. That is, if the test pin is low, then the microprocessor will continue its normal operation, or else if it is high, it will enter into the wait state, right? And this is an input is synchronized internally during the clock cycle on leading edge of the clock cycle, which means that for internal synchronization with the program, this pin is used to make the microprocessor to enter into the wait state, right? And the very important pin, next one is clock pin, where pin number 19, we know that it provides timing and clock signals. And when it comes to clock signals, in 8086, we have different versions of clock signal that can be generated. That is 8 megahertz, 4 megahertz, 10 megahertz. And depending upon the version of 8086, the clock frequency will vary, right? And coming to the ground and as well as supply pin, where VCC, we use 5 volt power supply for the operation of the internal circuit. And a ground pin, we have 2 ground pins in 8086, so that it reduces the power dissipation, right? So we use 2 ground pins. And the very important pin, as I said before, starting this pin diagram, is pin number 33, which determines the 8086 to enter into a minimum mode or the maximum mode. And I've already said what is minimum mode and what is maximum mode. In minimum mode, it will be acting as a single processor, whereas in maximum mode, it will act as a co-processor, where it will work in a multi-processor environment, right? And if this pin is high, if MNMX pin is high, it works in minimum mode, and if it is low, then it will be working in the maximum mode. And I have already said that in minimum mode, all the signals will be working, and in maximum mode, all the signals will be working, right? And minimum mode signals, as I said, these are the minimum mode signals, right? And whenever the MNX pin is connected to VCC, right, it will work in a minimum mode. Similarly, whenever it is connected to ground, it will be acting as a maximum mode, right? We will come to that little later, right? And the next pin is a DTR pin, which tells you data transmit and receive, right? It tells you the direction of data transmitted from the microprocessor. That is, whenever it is high, data is transmitted out of the processor, and whenever it is low, it is received. It receives the data. That is, data is received by the processor, right? And the next important pin is data enable pin, which is pin number 26. Whereas the DTR pin will tells you the direction of data, but the DEN pin will tell you whether there is a data or not, right? Whether there is a data to be received or transferred, it will be enabled by this particular pin, right? And it separates the data from the multiplexed address and data signal. That is, whenever there is a data, that will be indicated by this particular pin, right? And ALE, address latch enable. I have already said what is address latch enable. Address latch enable, that is used to demultiplex the address and data lines, and address as well as the address and signal lines. You can see here the AD line, that is address and data lines, and as well as these lines where this is address and status lines, right? Where whenever the ALE is equal to 1, right, it will demultiplex. That is, here the address and data lines is time multiplexed. Here the address and data lines is time multiplexed, right? And whenever the ALE is equal to 1, it will demultiplex these pins. Whenever ALE is equal to 1, it will demultiplex the address and data lines. Similarly, that is, whenever ALE is 1, this pin will be acting as a address line, right? And if ALE is equal to 0, then it will be acting as a data line. Similarly, here if ALE is equal to 1, this pin will be acting as a address line, and if it is ALE is equal to 0, then this will be acting as a status line, right? And you can see this is the demultiplexing operation that can be enabled using ALE, where by using different latches, right? When the ALE signal is enabled, we can able to demultiplex this and demultiplex this status line. You can see here these multiplexed lines has been separated into data bus, address bus, and status line, right? That is the operation of ALE. And similarly, we have pin number 28, that is M and IO pin. That is, it differentiate the memory access and IO access. Whenever it is high, it indicates that memory is accessed, and whenever it is low, it indicates that IO device is accessed, right? And write pin, similar to read pin, this is the write control signal, right? And whenever it is active, that is, we can able to write the data to the memory, right? The processor will write the data to the memory whenever it is asserted low. That is whenever it is active. Remember, we have WR, that is a bar signal, so it will be active whenever it is low, right? And similarly, interrupt acknowledge pin. We have already seen what is INTR pin and what is MI pin, the interrupt pin, right? And I already explained the relationship between INTR and interrupt flag, right? This is another important pin in corresponding to interrupt, that is INTA, interrupt acknowledge. That is, it indicates whether there is an interrupt or not. That is, if this pin is equal to 1, it indicates that the interrupt signal, there is an interrupt signal to the microprocessor, right? So that is the operation of interrupt acknowledge pin. That is, it just acknowledges whether there is an interrupt or not, right? And hold request pin. That is, whenever any particular peripherals or any masters requesting the processor bus request from the processor, that will be sent this particular pin. That is, only through this hold pin that we can able to request. That is, any peripherals or any particular device can request the bus access from the microprocessor, right? That is hold pin. And similarly, hold acknowledge pin, that is, it will acknowledge whenever there is a request from the peripherals or any devices to hold, that is, to access the control bus of processor, then it will be indicated by this particular pin, HLDA, right? So whenever it is high, the processor accepts the hold, right? That is the operation of HLDA pin. And the next one is, so far we have seen all different types of pins, and all this hold, HLDA, WR, DEN, ALE, INTA, everything are minimum mode signals. Similarly, we have maximum mode signals corresponding to this particular pin, and whenever the MX pin is low, that is, it is grounded, right, it will be working in maximum mode, whereas whenever it is connected to VCC, it will be acting in minimum mode, correct? Right. And the first thing is status lines. Similarly to these status lines, we have status lines here, right, which indicates the operation of the processor, right? That is S0, S1, S2, that is the maximum mode signals, where you can see here it tells you the different various mission cycles, status signals of various mission cycles. 000 represents interrupt acknowledge, 01 represents read IO port, and 10 represents write IO port, and similarly 11 halt operation, and this is code access. 101 represents read memory, and 110 write memory, and everything one is passive and inactive, right? These are the different status signals of machine cycles. And this is another important pin where the lock signal, which I already said that the hold pin, only through hold pin, the other peripherals will be requesting the bus, the control bus operation, that is, it will request the processor for control bus access, right? So when this lock pin is enabled, right, no, it will prevents any peripherals, any device that is accessing the system bus of 8086, right? And whenever it is active, whenever it is low, right, then it will mask all the interrupt as well, right? So this is like a locked state, right? So it will prevent the access of other peripherals or other devices that is accessing the system bus of 8086, right? And the other two status pins, that is QS0 and QS1, this is another status pin which will tells the status of the instruction queue. We have instruction queue in 8086, right? I'll explain that in architecture, where in 8086 you have instruction queue which will prefetch the instruction and it will store in that instruction queue, right? And this QS0 and QS1 will tell you the status of that instruction queue, where 00 represents no operation and 01 represents first byte of an opcode from the queue, and similarly 10 represents the empty of the queue, and similarly 11 represents subsequent byte from the queue, right? And the other important pin is similar to hold, right? This is where more or less the same like hold and hold A, right? When other bus masters request the processor, these lines will release the system bus, right? So after receiving the request, the processor sends the acknowledgement through this particular pin. And here you have two pins, that is RQ and as well as RQ GT0 and RQ GT1, where RQ GT0 is the highest priority, right, when compared to this one. And these pins have the internal pull-up resistor, right? So this is similar to the hold and hold A, but this is regarding to the maximum mode. Whenever microprocessor works in the maximum mode, then this will be giving the bus request and bus grant for the peripherals. And similarly, right now what we have seen is we have seen different pin configuration of 8086, and I have already explained about minimum mode and maximum mode. So you can see here these are the operations that is done in the minimum mode, and these are the signals that is used in the maximum mode. And there are common signals as well. I can see these are the common signals that is used in both the modes, where address and data, address status, bus high enable, minimum mode, maximum control, read control, wait state, right? All these are common signals, right? And similarly, we have separate signals for minimum mode and as well as maximum mode, where you can see these are the signals which I have already explained, right? These are the signals which is related to minimum mode signal, and these are the signals which is related to the maximum mode signals.
Thank you students, thank you for watching. கண்டிப்பா இந்த வீடியோ உங்களுக்கு எல்லாருக்கும் ரொம்ப யூஸ்ஃபுல்லா இருக்கும் நம்புறேன். Subscribe Passionate Professor and keep learning. Thank you very much.